Okay, so this video is about chapter 3, section point 2 and 3.3. So motion down a ramp. We're going to finish up vectors real quick. We talked a lot about them. We're going to go through this really quickly. Okay, so if anytime you have a vector, you can break it down into its x and y components and you add those together separately. We went through a detailed process of using vector components and adding two vectors together. So I'm not going to do that again right now. Okay, the absolute value of a vector, the x component is the magnitude of the component vector. The sign is positive if of x points in the x direction, and negative if it points in the negative direction. And the y is similarly. Okay, so vectors can be decomposed into component vectors parallel to the coordinate axis. Okay, and that's really important. When you have a vector, decompose it into its x and y components, and then you can add those together. Okay, that's really kind of the key is breaking it down into the components and then adding the different components together. Okay. And that's what they do here. They have a vector A going this way, and it's got a vector of AY and BY, and you can add those two together. Okay, if you have a vector, you can think of it as a triangle, right? You can always find the x and y components of it, and you can treat the magnitude like the hypotenuse of the triangle, okay? And that gives you the angle theta here. You have the magnitude, and then each component ax is equal to the hypotenuse times cosine of theta, and then ay is equal to a sine of theta. But it really is just a triangle, okay? And we use some trig in this class, but it's the same thing over and over. And so we're gonna look at this for a force, right? Going down a ramp. Okay, so we're gonna break a force vector into its x and y components, and so that's what we're doing here. Okay, just like a triangle. Okay, you can use the Pythagorean theorem. Okay, we actually did this last time. We did it a bunch. Okay, so this is just the Pythagorean theorem for the hypotenuse of our triangle, and you can similarly find the angle of the triangle like that. Okay, so we looked at this last time in great detail, but these diagrams are useful. This one, you have to think about it as a triangle that's rotated onto its side, but it's just a triangle. Okay. So what are the x and y components of this vector? Let's do some examples. Well, just looking at it, I can see that the tip of the arrow goes to 2 on the x-axis and 3 on the y-axis. Now, this is important because you can also describe a vector as two points, right? Two coordinates. So you could say this vector is a 2, 3 vector, 2 being on the x-axis and 3 being on the y-axis. Okay, so I'm gonna switch here, and we'll make a drawing of this. All right. So if I gave you a vector here, and I said I have a vector 2, 3, what does that mean exactly? Okay, because you could describe a vector like this is perfectly fine. Okay, well, this is my x component and this is my y component. Okay, we always do x and then y, and so it says x goes to 2 and y goes to 3. Okay, so then I go over here 2 and I go up 3, and there's my vector. Okay, that's it. And what's the angle of my vector? Okay, well, we can just use tangent of theta equals y over x. Okay, and then we're going to do arctangent. We've done that a bunch. So take the arctangent of both sides here. Uh, arctangent of tangent of theta gives us theta, and we'll take the arctangent of y over x here, and those values are 3 and 2. So I have arctangent of 3 over 2. And then I will switch to MATLAB. Where are you, MATLAB? There we go. Okay. And so in MATLAB, the command for arctangent is A10D. That tells it's in degrees because I don't have a degree setting this. Okay, so that's 56 degrees. Okay, so theta equals 56 degrees basically. Okay. All right, so we did that one. So for this one, the correct answer is B. We just look at the graph right there. Super simple. All right, what is the x and y components of this vector? Same thing. Okay, I look here quickly. I see that x is 3, and now let's see, y is I'm trying to turn on the video here. Okay, and y is -4. So x is 3 and y is -4. The answer is E then. Okay. All right, what are the x and y components of the vector C? Okay, well, now this is not located at the origin. Okay, so um, we need to think about this one a little bit carefully, okay? Because it's clearly the x component is -4 because I start at 1 and I go to -3, so that's a net amount of -4, and then I'm down here at -1, but I go up 1, 2, or I go up here 1 and then 2. Okay, so I think that the answer is -4, 2. I think it's D. Okay. Yeah, because we go over -4 and then up 2. All right. The angle that specifies the direction of the vector C. Okay. Well, so here's our triangle. Okay, and remember tangent is opposite over adjacent. Okay, and in this particular instant, they flipped it around here, and so they're calling it y, but that's really adjacent to the angle. Okay, so the y is going to go on the bottom, and then x is going to go on the top. And if we just want that angle there, then we need to make them positive, right? So it should be positive C and yeah, CX over CY. So I think it's D. Yeah, it is D. Okay. So they just called the axis Y instead of X. I mean, but you have to remember it's opposite over adjacent. Okay. And in this particular case, X is the opposite and Y is the adjacent. There's nothing special about X and Y. We could call the axes A and B. You know, it's what's important is opposite and adjacent. Okay. The following vector has a length of 4 units. Okay. What are the x and y components of that? Okay. Well, we know the magnitude is 4, and we also have we have an angle of 30 there. Okay, so we can do some trig now. Oh, okay. And let's right, so I'm gonna switch here. Stop. Then I will switch to all right. So the picture says, okay, we have a triangle like this. Okay, this angle is 30 degrees, and we know our hypotenuse is 4. Okay, this is our y-axis though. It doesn't really matter, and this is x. Okay, we just need to keep that straight. But y is yeah, it says what are the x and y components? Okay. Well, let's find our this one here. This side, this is our adjacent side. Okay. And so let's write down our formula. So it's going to be y equals our adjacent side is going to be r times cosine of theta. Okay. Now, usually you always, we're programmed in algebra that y equals sine, but in physics, we're trying to break you of that, okay? Because really, it doesn't matter what you call the axis, okay? Or the axis of the coordinate system, okay? Since this is adjacent, we're going to use cosine here. And so we have 4 times cosine of 30, and then our y component, well, actually the x component right here. So this part right here, this is the opposite side. So this is going to be x equals r times sine of theta. Okay, and I think they intentionally flip this around on you just so that you get rid of this attachment to, um, x and y because they're not special. Okay, so this is 30. Okay, so let's go into MATLAB and I'll plug both of those in really quickly. Okay, so MATLAB, here we go. All right, so I'll do the y component first. It's going to be 4 times cosine d of 30. Okay, so that's going to give me, for my y component, 3.4641. And then for my x component, we said sine of d. And I put the d there so that it's in degrees, okay? And I get an answer of 2. Now that seems really unphysical. So what did I do wrong here? Sine of D. Oh, no, actually that's that's not unreasonable. This is just the length of the side. Okay, that could be true. And it should be negative. Okay? I think it's negative. So this is -2. Let's go back and see what it was asking us for. Yeah, it's going to be -2 because we're going over here this way. Okay, so it's going to be -2. Okay, so x is -2 and y is 3.46 or 3.5. And so it looks like the answer is B. All right. Oh, we got another one. Okay, same thing. Okay. Following vector has a length of 4 units. What are the x and y components? Okay, well we already have the answers for this one. Okay, well we figured out what sine and cosine of 30 are times 4, right? But we got a different orientation here for our vector. All right, so we're gonna have to deal with that. Okay, still still 4 long, okay, but now I can just look at this. I already know what this is, okay? This side is -2, and this side is -3.5 because I did this triangle, right? We just did the triangle, okay? And now it's pointing down clearly, so -2. This one's pointing in the negative x direction, so up here this one was -2, but this one was 3.5. Okay, that's what I got from MATLAB over here. Okay, so for this one, then if I write it in the two coordinate system, it's going to be -3.5. That's my x component, and then here I have -2. Okay, so and yeah, I already know the answer, and so the answer is -3.5 and -2. The correct answer is E. All right, moving on. Sweet. Example, finding the component of the acceleration vector. Find the x and y components of the acceleration vector of A shown in the figure. Okay, well, same thing, okay? Now it's the components of the acceleration, right? Because we are accelerating in a certain direction here. Okay, so our magnitude is 6 meters per second, and our angle is 30. Okay, so I'm going to redraw this. And even for this stuff, when I have a diagram, I like to redraw it, okay, because it helps me to think about the problem. I think when you draw a picture of it, it it gets your brain working. You're using a different part of your brain now. You're using the visual parts. Okay, so we can find our components of this. We're supposed to find the X and Y components. Okay, so we just do the same thing. Okay, so right here, if we want to find our X component, it's the adjacent side here. Okay, so I'll have my acceleration in the X component. Okay, my hypotenuse is going to be 6 meters per second squared. And then since this is adjacent, it's going to be cosine of 30. Okay, and then I'm just going to go ahead and write down AY right now. Maybe I should write down the uh, yeah, in symbolic form first. Cosine of my angle theta. So AY is going to equal R sine of theta, or it's going to be 6 meters per second squared times sine of 30. So that's going to be right here. It's going to be this part. Okay. So up along this part, this is AX equals R cosine of 30. And now over here, I need to add my the correct sign. So I'll say this is pointing down. I'm looking at it and I can see, okay, it's pointing in the negative direction. So this will be A times oh yeah, this should be uh yeah, AY is going to equal minus A times sine 30, and that should be an A right there. Okay, so now we just need to put this into MATLAB. And this isn't too bad. All right, where's MATLAB? Okay, so similar answer. I'll just grab this one, and now my magnitude is 6 instead of 4. Okay, so that was my Y component here. So I'll write that down and say AY equals 3 meters per second squared. And now I'll do cosine, and I do sine D, so it's in degrees, so cosine D of 30. Okay, so then AX is going to equal 5.1962 meters per second squared, or I could just call it 5. Okay. All right, so what do we got here? Yep, they did the same thing. We got the right answer, and yeah, uh those are both negative. Yes, we forgot the negative sign there. Those are both negative because it is pointing downwards and to the left. So those are both negative. All right, we can add vectors using components. We did this in the last video. So you take your vectors, you find the component of X and Y, then you add the X components to the X components and the Y components to the Y components. Go back and watch the last video because we did a very detailed job of that. Okay, so AX is the blank of the vector AX. Well, it's the magnitude. Okay, the following vectors have lengths of 4 units for each vector. Okay, for each vector, what is the component? Parallel the ramp. Okay, so let's look at this last problem here because it directly relate into the next section that we're going to do. Okay, so what if you have a, a ramp like this, okay, at some angle, and then we also have, say, a vector here on the ramp, okay, or yeah, and we'll call this vector P, okay, and the problem asks us find the components along the ramp. Okay. Now, that might seem strange, but what we're usually going to do is we're going to break this into two coordinate system. Okay. And we're going to do a little shift here, and we're going to say that down the ramp is positive X. Okay. And perpendicular to the ramp is positive Y. So we're going to flip our coordinate system, okay, to make the problem easier because it really doesn't matter where the coordinate system is or what you call it. Okay. All we care about is how do we make the problem easier to solve or even solvable sometimes, okay? So it says find the component of the vector p along the ramp. This is kind of a tricky problem at first, okay? We're going to do this in a minute with gravity, okay? We need to find the component of the vector p around it, along the surface of the ramp, okay? And this has a lot of applications. So we're going to do this, okay? So our in their new bases here, x and y, we're rotated. We can find the components of p, and we've already been doing it, okay? So now the key here is, okay, and this is something that you need to recognize and just accept it, okay? The angle here, theta, is going to be the same angle here. So if I tell you the angle theta here, it's that angle, okay? So now we've got a right triangle here, okay? And we've got the same angle, okay? So if we want to find P, okay, now, okay, we're going to take, here's our angle. We're going to take the opposite side over here. So this is going to be P times sine of theta, and we're going to call this, this will be P of X. That's our component in the X direction. Over here, okay, this is going to be PY, and it's going to be P times cosine of theta. Okay, so that's how we do it. And we're going to do this a bunch for different problems. In fact, let's look at an example right now. All right. What better than to do an example? Okay, hopefully you saw a video of me skateboarding down the parking garage. Okay, now here's the thing about parking garage. Okay, when I ride my skateboard on the parking garage, um, it is a little bit scary. You know, I'm not as young as I used to be, but I know that there's a lot of friction. Okay. I do snowboard sometimes, not very much in Missouri, but there is a snow hill here you can go snowboarding on. And so when I snowboard, I know that there's a component of gravity that's pulling me down the hill, right? The thing that makes me go down the hill or the parking garage of my skateboard is gravity. Okay, but it's not straight down. Okay, so here is I found Charmander. He's gonna be my new assistant. Don't be jealous, Pikachu. Okay, don't worry, Charmander and Pikachu are my buddies. Okay, so if Charmander's here, right? If his acceleration just falls straight down, okay, um, that's different than if Charmander is sliding down a ramp. Okay, I need a ramp. Hold on just a second. Okay, so we have a ramp here now, and a lot of people don't know this. Zoom out. Thank you, Siri. Okay, but Charmander is a very deep sleeper. Okay, and he won't notice if he starts to slide down the ramp. Okay, now I've got my inclined ramp here, and see, people ask, why, how do things slide down an inclined plane? I would ask maybe why an inclined plane. Okay, so this is pretty steep here, and Charmander has a lot of friction between this ramp here. Okay, and so he is not go. Oh, there we go. Okay, so see that when I hit that critical angle, he starts to slide down the ramp. Okay, but it's pretty high there. Okay, and so there's a component of gravity that is making him slide down the ramp. Okay, it's not just mg, right? So here's the angle. Okay, and when the force of gravity gets stronger than the force of friction, he will start to slide down the ramp. No, Charmander, stop! Oh, oh, are you okay, Charmander? Oh, Charmander. Oh, he's okay. Don't worry, buddy. We'll put him over here. Then we'll just hang out over here. Good job, Charmander. Okay, Charmander's there. So there's a critical angle that Charmander will start to slide down the hill, and his acceleration, the force due to gravity, has to get big enough. Okay, so let's talk about um, this force. It is Charmander. All right, so Charmander is, let's say he is sliding down a hill because he loves to have fun. Okay, so here's Charmander. Okay, he's sliding down the hill. Okay, so how do we find the acceleration here? Let's say this is 30 degrees. Okay, we know that gravity is pulling Charmander down here. Okay. Um, but he's not going to fall straight down, right? He doesn't fall at 9.81 meters per second squared. If this is a slight incline, he's going to accelerate much slower than that. Okay, so we need to find that component of acceleration. And so what you do is you say, okay, the acceleration due to gravity is the hypotenuse of my triangle. And so what am I going to do? I'm going to make another triangle here. First, start by drawing the perpendicular line here. This is the base of my triangle. Okay, that's my base. And then here's my opposite side. Okay, so this is opposite and this is adjacent. And this is really important. This angle here is also 30 degrees. Okay, those are the same angle. Okay, and if you know that, because all the problems that you see, they're going to give you this angle here and they'll say, find the acceleration down the hill. Okay, all right, so that's not too bad then. Now we already saw the formula. Okay, so it's just a component of acceleration on this side. This is the opposite side. Remember? You can just take my triangle here. Oh, I've got a triangle. This is the opposite side here. I'm going to write that down over there. Okay. So this component right here, okay, right there, that part of my triangle is the opposites. Okay. And remember, I'm going to define positive x as going down this way. Right? That's positive x. Yes, it's going down and to the left, but you know what I can call positive x whatever I want to. Okay? It really doesn't matter. I could have drawn my picture the other way, but I drew it this way. I'm saying that way is positive x. Okay? So, and my component here, I'm going to call ax. That's my x component because it's going to be parallel in this direction. Okay? And then the hypotenuse is going to be g. And so now I've got sine of theta there. Okay, that's my acceleration. So to find my acceleration then, it's going to be 9.81 times sine of 30 degrees. All right, let's plug that in. How fast is Charmander accelerating? Is he like, or is he more like, eh? Yeah, I think it's more like the second one. But let's just go to MATLAB and we will calculate it. All right. So now we said we have 9.81. I always throw the one in there. It's technically correct. You could just do 9.8. I mean, you could even do 10 if you wanted to. Okay, sine of 30. Okay, it's 4.91. Now let's recall, maybe you don't recall, I don't know. But sine of 30 is it's 1/2 actually. Okay, so if you know that value, a long time ago, well, actually maybe not that long ago, but when you take math, you used to have to memorize these tables of different values. I, of course, never memorized it, but it's actually useful to know. So sine of 30 is 1/2. Sine of 45 is, okay, that's not so easy to remember. 0.7, I think that's actually 1 divided by the square root of 2. Yeah, it is. Okay. So those are just some useful identities. We've also got sine of 60. Okay, so that's what is that one? Okay, I don't remember what that one is, but it also had some convenient identity. Okay, so those are just some easy values to remember by. Okay, but we had sine of 30. Okay, so sine of 30 times 9.8, 1. Okay, so 4.95. I'll write that down. So my acceleration in the x direction is going to be 4.9050 meters per second squared. Okay, so let's see. So that is Charmander's acceleration in the x direction, or we could just write x equals 4.9 meters per second squared. Okay, so what did we do? All right, we created a new axis system and we said positive x is going down the hill. Thank you, Bulbasaur.